So how much do you earn?
42 lakhs per annum.
Mental health emotion detection is a powerful project for AI and ML students who want to build technology that genuinely helps people, and I want you to see how impactful this can be in real-world healthcare. Imagine an AI system that listens to someone's voice, reads their messages, or analyzes their facial expressions and understands whether they are stressed, anxious, sad, or emotionally overwhelmed. That is the core idea behind this project, and it uses simple NLP, speech processing, and computer vision techniques to identify early signs of emotional distress. This matters even more between 2025 and 2027, because mental health awareness is growing, yet many people still lack access to timely support. AI can fill this gap by offering continuous monitoring and early detection. You can apply the system to social media platforms, to flag distress signals, to therapy tools that help professionals track patient emotions, to corporate wellness programs that monitor burnout, or to telehealth platforms that analyze emotions in real time during online consultations. These applications make the project extremely relevant for companies hiring in mental health tech, telehealth, wellness platforms, and healthcare AI. Recruiters value this project because it shows you can work with sensitive data, understand emotional cues, and build AI that enhances human well-being. Understanding the skills needed for mental health emotion detection is important because this project blends NLP, speech processing, and computer vision, and recruiters want candidates who can work across these areas with confidence. And you begin by learning sentiment analysis, so the system can read text and understand whether someone sounds positive, negative, or emotionally distressed. You also study transformer models like BERT, because they help detect subtle language patterns related to depression or anxiety. Next, you explore speech processing, where you extract features like pitch, tone, and speaking rate to identify emotions in a person's voice. Tools such as Liberosa help you capture these variations in audio. On the vision side, you learn facial expression recognition, micro-expression detection, and facial landmark analysis, using libraries like OpenCV and DLib, which help the AI interpret nonverbal cues. These three skill domains form the foundation of emotion detection. You also use frameworks like Hugging Face, PyTorch, and TensorFlow to build and train your models. For text, tools like SpaSci and NLTK help with pre-processing. Along with technical knowledge, you need strong understanding of mental health terminology, ethical AI practices, privacy requirements, and bias mitigation. This project teaches you to work responsibly with vulnerable users, and recruiters value these skills because they show you can build AI that is technically strong, empathetic, and safe. When you build a mental health emotion detection system, you need a clear roadmap, because this project involves multiple data types, and recruiters want to see that you can structure complex AI workflows from start to finish. You begin by choosing your detection modality, which means deciding whether your system will analyze text, voice, facial expressions, or a combination of these. This choice depends on your use case and the kind of data you can access. Next, you gather training data from mental health datasets that include emotion labels, facial expressions, or depression indicators, and you handle this information with extra care because it is sensitive. Once you have the data, you move into core model development. For text, you fine-tune models like BERT so the system can detect emotions and signals related to mental distress. For voice, you extract acoustic features, such as tone and pitch, to train classifiers. For faces, you build CNN-based models to recognize expressions. Then you combine everything into a detection pipeline that includes pre-processing, model inference, confidence scoring, and alert mechanisms for critical situations. After this, you test the system ethically, by checking fairness across different groups, validating your approach with mental health experts, and ensuring safeguards against misuse. Finally, you deploy the system with encryption, continuous monitoring, and user-friendly interfaces. Beginners usually take 8 to 12 weeks, while intermediate learners need 5 to 7. Completing this roadmap shows employers that you can build sensitive, reliable AI systems for mental health care. This project creates strong career opportunities because emotion-aware AI is becoming essential in mental health support, telehealth, and wellness platforms, and companies need engineers who can build systems that understand human emotions in a safe and responsible way. When you complete this project, you can target roles such as mental health AI researcher, emotion AI engineer, or healthcare NLP specialist. These positions focus on building advanced detection models that analyze text, speech, or facial expressions, and they often require the ability to work with multimodal data. Recruiters expect you to understand mental health indicators, follow ethical AI practices, and handle private information carefully. They also look for cross-functional skills because you may collaborate with psychologists, clinicians, or product teams. Your resume becomes stronger with keywords like emotion detection, effective computing, sentiment analysis, and multimodal AI. Companies like Woobot, Weeza, Ginger, Talkspace, BetterHelp, Spring Health, and several telehealth startups hire engineers with these skills. Salaries are attractive, with freshers earning 8 to 16 lakhs in India and professionals with a few years of experience reaching 18 to 32 lakhs. In the United States, entry-level roles often range from $90,000 to $140,000 because this field requires niche expertise and deep responsibility. Building this project shows that you can create AI that supports real human well-being. Start building this today and put it on GitHub.
I can teach you code in Python in just 30 days, even if you've never written a single line of code before. How? Simple. In my 30-day Python using AI bootcamp, you don't learn to code the hard way anymore. You learn to think like a developer and let AI do the heavy lifting. I'll show you how to use AI tools that senior developers are already using every single day. Tools that write code for you, explain errors in plain English, and turn your ideas into working projects fast. Day 1, you're building your first script. Day 15, you're automating real tasks. Day 30, you have a portfolio that actually gets you hired. No CS degree, no coaching institute, no 6-month course. My students, people who were in your exact position, are now working as Python developers, data analysts, and AI automation specialists, pulling 18 to 25 lakhs per annum, not because they memorize syntax, but because they know how to build with AI. This is the skill companies are desperate to hire for right now, and it's only getting more valuable. So click the link below, join the 30-day Python using AI bootcamp for just 199 rupees. Seats are limited, register now before it fills up.
How do you monitor GPU utilization and cost in cloud AI workloads? Understanding this question is like watching how hard a race car engine pushes while seeing how fast the fuel bill climbs. Performance and cost move together, and even small inefficiencies can create large expenses over time. Utilization shows how much real work the hardware is doing. Imagine an assembly line where workers pause between tasks. Everything slows even though you're still paying full price. GPUs behave the same way when workloads don't keep them active. VRAM usage reveals how well the model fits inside its workspace. Underuse means you're missing opportunities for larger, more efficient batches. Overuse leads to stalls and instability. Cost closes the loop. Cloud billing ticks forward like a taxi meter. When utilization falls behind, the meter keeps rising, which is why production teams constantly track these signals together. A strong interview answer is, I monitor GPU usage, VRAM behavior, and hourly cost together because they reveal true efficiency. If someone asks what usually drags utilization down, you can say, slow data pipelines starve even the fastest hardware. Core monitoring in the cloud is about aligning performance and cost so they rise together. This balance works the same way a well-run kitchen manages timing, ingredients, and effort. When everything is aligned, the entire workflow feels steady and predictable. Real-time metrics offer the first clues. They show utilization, temperature, and VRAM activity, much like checking a heartbeat to see how consistently the system is working. Cost tracking adds the financial dimension. Each hour of training carries a real price, and any slowdown quietly raises that number. Watching cost beside performance helps you spot inefficiencies before they compound. Resource optimization ties the picture together. Right-sizing hardware, using spot capacity when the workload allows it, and eliminating idle cards is like adjusting kitchen staffing to match the pace of the meal. Together, these layers create meaningful efficiency. An interview answer might be, I combine real-time metrics, cost visibility, and right-sizing to prevent waste. If asked what alert you enable first, you can say low utilization under 50%. You're developing reliable production instincts. Monitoring GPU workloads depends on the tools that reveal behavior at different depths. Each tool contributes a unique perspective, the way pilots rely on separate instruments for altitude, heading, and engine health. NVIDIA SMI gives you instant insight into utilization, temperature, and VRAM activity. It acts like a direct dashboard for understanding how the hardware feels moment to moment. DCGM expands this view across many cards. It exposes fleet-wide patterns so you can see issues that only appear when many GPUs work together. TensorBoard brings training behavior into focus. Throughput, loss curves, and progression over time help you understand whether learning is healthy or drifting. Cloud tools like CloudWatch, Azure Monitor, and GEE-CP monitoring add the financial dimension by tying performance signals directly to billing. Key metrics bring everything together: utilization for workload intensity, VRAM usage for batch sizing, cost per hour for burn rate, throughput for end-to-end speed, and idle time for starvation detection. An interview-ready answer is, I track utilization, memory use, throughput, idle periods, and cost to locate real bottlenecks. If asked which signal matters most, say throughput because it reflects the entire system. You're sharpening your intuition well. A production ML pipeline feels smooth when each stage supports the next. Seeing the entire journey, from data to deployment, makes it easier to understand where performance and cost originate. Ingest pulls raw data into the system the way materials arrive at a factory before assembly begins. Pre-processing prepares that data, like sous chefs cleaning and organizing ingredients so the rest of the workflow stays efficient. Training is where the GPU performs its heavy lifting. If data arrives too slowly, even powerful hardware sits idle, silently wasting money. Validation checks the model's behavior before release, much like running a test flight to ensure a plane performs safely. Deployment places the model into real use where reliability and speed matter. Any delays at this point ripple outward into user experience. Cost stretches across all of these stages. A strong interview answer is, I monitor GPU behavior during training and track cost across the entire pipeline to keep delivery predictable. If asked where issues appear most, you can say ingestion and pre-processing often hide quiet bottlenecks. You're connecting these pieces exactly the right way. Interviewers love exploring how you think about cost, performance, and stability in GPU-heavy systems. These follow-ups reveal your practical judgment more than your raw knowledge. Reducing cost without slowing performance often involves smarter compute choices. Spot instances, auto-scaling, batch jobs, and mixed precision work like more efficient tools that boost productivity without reducing quality. Alerts create early awareness, low utilization, budget thresholds, VRAM overflow, and training errors behave like cockpit warning lights that help you respond before problems escalate. Comparing GPU and CPU value means thinking in cost per epoch or time to convergence. A GPU may cost more per hour, but if it finishes 20 times faster, it delivers far more value. Multi-card monitoring keeps distributed training coherent. Imagine several GPUs passing gradients like notes around a table. If one slows down, everyone waits. Tracking per card throughput keeps the circle moving smoothly. These questions test real operational thinking. A polished answer is, I combine spot use, mixed precision, utilization alerts, and per card throughput to balance cost and performance. If someone asks about common mistakes, say many people optimize the model but ignore communication overhead. You're mastering these ideas quickly. Thanks for watching this AI/ML interview series. If you found these insights valuable, please like this video. It helps others discover it. Feel free to comment with any interview questions you'd like me to cover next. And don't forget to subscribe so you never miss the next module. If you know someone preparing for AI or ML roles, sharing this video could make a real difference for them.
When interviewers ask for the difference between AI, machine learning, and deep learning, they want to see if you understand the structure behind modern AI. Here is the cleanest way to explain it. AI is the broad field of making machines behave intelligently. Machine learning is one part of AI. It helps systems learn patterns from data instead of following fixed rules. Deep learning is a more advanced form of machine learning. It uses many layered neural networks to understand complex information like images, speech, and text. A strong interview answer is AI is the big idea. ML is the data-driven approach inside AI. Deep learning is the powerful technique inside ML that handles complicated patterns. Think of YouTube. AI controls the whole recommendation engine. ML predicts what you might click next. Deep learning studies thumbnails, speech, and video content. This simple hierarchy becomes the foundation for many interview questions. Keep it clear, and you will stand out. Now imagine the visual on this slide is 3 clean layers stacked on top of one another. At the top is artificial intelligence, the broadest idea. Inside AI sits machine learning. It learns from data. Inside ML sits deep learning. It learns features directly from raw inputs. A smooth interview explanation is: AI is the broad field. ML is the data-driven method within AI. Deep learning is the neural network technique within ML. This hierarchy helps you choose the right tool. ML is great when patterns are structured and data is limited. Deep learning shines when the data is rich and complex. A self-driving car shows this clearly. AI decides actions. ML predicts how other vehicles move. Deep learning reads camera images and identifies lanes and objects. Once you explain the hierarchy, interviewers often check if you understand how real systems are built. This slide shows the common ML workflow. A practical pipeline starts with data collection, then cleaning, then creating features. After that comes training, then deployment, and finally, monitoring the model in production. A simple interview answer is data collection, feature creation, model training, deployment, monitoring. A real example is fraud detection. You gather transaction history. You create behavior features. You train ML or deep learning models. You deploy them to check each transaction in real time. You monitor accuracy and drift. Interviewers may ask, how much data does deep learning need compared to ML? When is deep learning unnecessary? What are the compute costs? Keep your answers grounded in reality. ML is lighter and easier to explain. Deep learning is powerful but expensive. This view shows that you think like an engineer. This slide brings everything together. Each technique solves a different kind of problem. AI handles decision-making and rule-based tasks. Machine learning handles prediction tasks. like recommendations, spam filters, and forecasting. Deep learning handles high-dimensional data such as images, audio, video, and natural language. A strong interview summary is: AI is for intelligent behavior. ML is for prediction. Deep learning is for complex patterns and rich data. Think of real examples. AI powers chatbots and robotics. ML powers fraud detection and ranking systems. Deep learning powers face recognition, speech-to-text, and autonomous driving. Interviewers may ask, why does deep learning work so well for images? What ML projects have you built? How do you balance accuracy and speed? Use simple logic. Deep learning learns features on its own. ML relies on features you design. You have now mastered the core difference between AI, machine learning, and deep learning. When you understand this structure, interviews feel more predictable and less stressful. Keep your explanations clear. Use real examples. Stay calm and confident. You already have the foundation that many candidates miss. If this helped you prepare, subscribe for more interview-friendly guides. Like and share to support others learning these topics. Comment with the next concept you want me to explain. This slide introduces the 3 major learning types in machine learning. Many candidates mix them up, so let's make it simple. Supervised learning means the model learns from labeled examples, just like a teacher showing the right answers. Unsupervised learning has no labels. The model looks for natural patterns on its own. Reinforcement learning is learning by doing. The agent tries actions, receives rewards, and improves through experience. A strong interview answer is: supervised uses labels. Unsupervised finds structure. Reinforcement learning learns behavior through trial and error. A real example is a smart assistant. Supervised models classify speech. Unsupervised models group user behavior. Reinforcement learning improves action choices. Interviewers may ask, when do labels matter? Why does clustering help? How does an oral agent explore? Short answers. Labels guide prediction. Clustering reveals groups. Exploration helps find better strategies. Here we go deeper into supervised learning. Think of it as pattern learning from clear examples. The model receives input and the correct output, learns the mapping, and predicts new labels. A clean interview answer is: supervised learning uses labeled data to solve classification or regression tasks. This works because known outputs let the model learn precise relationships. A real example is email spam detection. The model sees many labeled emails and learns what spam looks like. Supervised learning powers price prediction, medical diagnosis, quality scoring, and many everyday ML systems. Interviewers may ask, what is the difference between classification and regression? Why is label quality important?